Hi everyone, I'm here to show you a very important theorem in mathematics called the average value of a function, otherwise known as the mean value theorem for integrals. So it goes like this. We start with a continuous function above the x-axis on a closed interval a,b. And recall that when a function's continuous on a closed interval, it's guaranteed to have an absolute minimum and an absolute maximum y value. So we call the absolute minimum y value little m, and on my graph, it looks like it's around here. That looks like the minimum. It could be at an endpoint, but I deliberately drew it this way. So let's call this horizontal line y equals little m. The absolute maximum value looks like it's here, and we'll call that y equals capital M. Okay, so in order to motivate what the mean value theorem for integrals is, what we do is we talk about the actual area under the curve on AB. So it's this area I'm shading in here. Okay. And that area is represented as the definite integral from a to b of f of x dx. Now, we're going to take a look at two rectangles. We're going to look at the rectangle formed by the minimum value. So let's take a look at this rectangle, this red rectangle. Now, the area of the red rectangle can be represented as the height, which is little m, times the width, b minus a. That's also represented as the area from a to b of the horizontal line, little m, with respect to x. But if you recall from our properties of definite integrals, we said one way to evaluate the definite integral of a constant is to take the constant and multiply it by b minus a. We could also use the first fundamental theorem of calculus to show that. Okay, now let's take a look at the area of the yellow rectangle formed at the maximum. So I'm going to try to outline that rectangle here. And that area is this one. I'm shading in this way. So the area of the yellow rectangle is its height, which is capital M, times the width b minus a. And that too can be represented as the definite integral from a to b of capital M with respect to x. Now, the next step is to compare the areas, the actual area under the curve, this area, with the area of the red rectangle formed by the minimum and the area of the yellow rectangle formed by the maximum. And we can see that the area of the red rectangle, which is little m times b minus a, is certainly less than the area under the curve. And the area of the yellow rectangle is certainly more than the area under the curve. So I'll put that here. So what we're saying is that the area under the curve is bounded by the area formed at the absolute minimum and the area formed by the absolute maximum. Notice that it would make sense to say, and it would appear that there must be rectangle there must be some rectangle with a height between the absolute minimum y value and the absolute maximum y value, so that its area is equal to the area under the curve, under F on AB. Okay, it would make sense to say that. If we divide each side by b minus a, which is non-zero, so I will do that here. Let's divide this side by b minus a, and this side by b minus a, and this side by b minus a. We get that little m is less than 1 over b minus a times the definite integral from a to b of f of x dx, which is less than capital M. So this is the minimum y value. This is the maximum y value. And this must be the special y value, or height of the rectangle, so that its area under the interval from a to b is equal to the area under the curve. All right, so here we introduced many ideas, and I think it would be appropriate to talk about how we would get this special y value. Well, there are infinitely many y values from a to b under this curve. It would make sense that this special y value is the average of all possible y values. So let's prove that on the next page. So, okay, well actually, why don't I just state the mean value theorem for integrals. So this is the statement. The mean value theorem for integrals almost like the mean value theorem for derivatives, it guarantees a special number c in the interval. So it says that if f is continuous on a closed interval AB, there exists a number c, at least one number c, inside the interval from a to b, so that, oh wait, let me just, okay, sorry for that interruption. So that the definite integral from a to b, oh, sorry about that, I lost my pen. F of x dx. The area under the curve is exactly equal to the area of a very special rectangle. F of c would be the height of that rectangle. And b minus a is the width. It's always, the width is always b minus a. Okay. And this special y value, which has to be obtained from that c value we find, is called the average value of a function. And let's just define that now and we'll prove it. So that the average value of a function f which of course is continuous on AB, is defined to be f of c, which sometimes we call f with a subscript of av, and that is 1 over b minus a times the definite integral from a to b of f of x dx. So what we just did here is we divided each side of this equation by b minus a to isolate f of c. And when we isolate f of c, which is so important, we call that the average value of the function. Okay, now I'd like to show you that the average value, prove that the average value of a function is equal to the average of all the y values on AB. So let's proceed this way. Actually, we should say that the average value, or this f of c, is the average of infinitely many y values on AB. Okay, so we proceed as follows. We divide the interval AB into n subintervals of equal width. And we'll list the subintervals as, and of course, equal width is delta x is b minus a over n. I mean, that is the theme in everything that we do. So we'll divide the intervals in the interval into n subintervals of equal width, and we'll call the subintervals a x1, x1, x2, x2, x3, and we continue until we get to x sub n minus 1b. And what we'll do is we're going to choose arbitrarily an x value in each subinterval. And because this x value is special, I'll choose x1 star in the first subinterval, x2 star in the second subinterval, x3 star in the third subinterval, all the way to xn star in the last subinterval. And now that we've chosen them, we're going to get their corresponding y values. So the y values would be f of x1 star in the first subinterval, f of x2 star in the second subinterval, f of x3 star in the third subinterval, finally to f of x sub n star in the last subinterval. And what we will do is we're going to find the average value. We're going to show that the average value f av is the average of these ny values. And to find the average of ny values, we simply add them all up and divide by n. So we'll do f of x1 star plus f of x2 star plus f of x3 star plus ... to f of xn star, and divide that by n. This is how we get an average of a finite number of values. You'll see how the limit comes in very soon. And we're going to use a little bit of an algebra. Since delta x is b minus a over n, if I put delta x over 1, I could rewrite this as 1 over n is equal to delta x over b minus a, okay, by properties of proportions. So factoring out the 1 over n, okay, I'll just put a cloud here so you remember. So factoring out the 1 over n and getting this, I will replace this with delta x over b minus a. Okay, so f av is equal to f of x1 star delta x plus f of x2 star delta x plus f of x3 star delta x all the way to plus f of xn star delta x all divided by b minus a. Now, if we look at the numerator, we have a Riemann sum. It's not a left sum or a right sum, but it's still a Riemann sum. So we could abbreviate it as follows. Using sigma notation, I could write the summation from k equals 1 to n of f of x sub k star, where k varies from 1 to n, times delta x, divided by b minus a. And now we have the power in calculus to take the limit of this expression. And if we want to sum infinitely many Riemann sums in this form, we have the limit as n increases without bound of the summation from k equals 1 to n of f of x sub k star delta x. The b minus a, dividing by b minus a is a constant, so it just goes outside the limit. And if you notice, this is the definition of a definite integral. So the average value of a function is indeed the average of infinitely many y values on the interval from a to b on f of x. And that would be the proof. So I thought that was a very nice proof. And we should definitely memorize this formula because it is often asked at least once on the AP exam. And I'd like to show you a few problems. Okay, so the first problem will be algebraic. And it goes like this. 1, if f of x is a function 3x squared minus 2x. Part A says, find the average value of f on AB. So here we just use a formula. Oh, I didn't give you AB, on the interval from 1 to 4. Okay, so A is 1 and B is 4. So this integral becomes 1 over 4 minus 1, the definite integral from 1 to 4 of 3x squared minus 2x dx. Okay, so now we work this out. We anti-differentiate 3x squared, which is 3x cubed over 3 minus 2x squared over 2 by the power rule. We don't need a plus c from 1 to 4. This is abbreviated as 1/3 of x cubed minus x squared from 1 to 4. According to the first fundamental theorem of calculus, we substitute 4 into the antiderivative. and then the 1 and subtract. So please copy it the way I have it. And we compute, and we get 1/3 of 60, well, wait a minute, 4 cubed is 64 minus 16. And this one just gives us 1 minus 1, which is just a 0. So our answer should come out to be 16. And that's the average value of the function. This is a y value. But part B says, find the values of C guaranteed by the mean value theorem for integrals. So what we have to do now is take our average value, 16, which is our y value, f of c, and make it equal to f of x, which happens to be 3x squared minus 2x. So here we're using the y value to find the x value. So we solve this equation, we bring the 16 over and make a quadratic equation in standard form. This is factorable into 3x, well, I should put c here, but the x and c are the same. 3x minus 8 times x plus 2 equals 0. So 3x minus 8 equals 0, or x plus 2 equals 0. So here x is equal to 8/3, which is in our interval. But on this side, we get x equals -2, not in our interval, so we reject it. So the answer is x equals 8/3 for that piece. Okay, I wanted to take a look at another problem with you and highlight a very, very important idea. Now, this problem is given in context, and I'll write it down. C of t is the daily cost of air conditioning in the house in dollars per day. So this is a rate of change. T is the time in days and t equals 0 corresponds to July 1st, 2017. And then the question is, explain what these expressions mean. In real world terms. Including units. Okay, I like this analogy very much. The first one is the definite integral from 0 to 90 of c of t dt. Oh, I made a mistake there. I meant c of t dt. Let me just erase this here and correct it. And the second one is 1 over 90 minus 0 of the definite integral from 0 to 90 of c of t dt. Very important difference in the units. Okay, now if we take a look at the first integral, this is the integral of a derivative. And according to the total change theorem, if you think about it, if this unit is dollars per day and dt is days, this would represent the total cost to cool your home from July 2017 to September 2017 in dollars, okay? Because notice that the days cancel out and we get dollars. Whereas in the second integral, this 1/90 changes it. Because if we have dollars per day times days, and then we multiply that by 1/days, the unit, notice that these days and these days divide through, and we're left with dollars per day. So when we have average value, this is the average cost. All right, so we have, this represents the average cost to cool your home in dollars per day from July 1st, 2017 to September 2017, because from July to September, in both cases, that's 3 months from then. Okay, so what I'd like to emphasize here is that when we just have a definite integral of a derivative, we have total change. Think of the units. Whereas if we have average value of a function, the units are the same as the function that's being integrated, which is c of t. Okay, so remember that whatever's after the integral in average value, those are the units we use. Whereas if we have the total change theorem, we have to think of our units very, very carefully. So I wanted to go over that with you. And let's just do one more for practice. For practice is this one. If R of t, the wrong color again, R of t represents the rate water is pumped into a lake in gallons per hour, and T is the number of hours, explain using correct units the meaning for of this expression. Okay, pause the video and then restart it to check your answer. Okay, so the answer to this is that it means the average rate in gallons per hour water is pumped into the tank, into the lake, I should say, into the lake in the first 6 hours. Or you could say from t equals 0 hours to t equals 6 hours. But make sure you have the unit, the explanation in context, and the time. All right, that takes care of average value. I hope that that this will answer any question in the homework, and we'll speak to each other soon. Take care and stay well. Bye.